Hi class, today we're going to be discussing section 11.2, dealing with identification spaces. Now you'll want to take a look at the book of proof on pages, let's write this down, pages 201 to 203, 205 to 208, and 210 to 213 here to read through this a bit more in detail. But we will do a recap, and we will start with the definition of a relation. So a relation on a set X, the book of proof uses A, but I'm going to stick with X because we've been traditionally using the space, the topological space X. So X is a subset, we'll call it R, of the Cartesian product X cross X here, and we often abbreviate the idea that xy, so remember, if the relation is a subset of the Cartesian product, then we're ordered pairs here, but a lot of times we'll use this symbol here, and we will read this as X is related to Y. Okay, so let's consider an example here. So consider the set R, which is X, Y in Z cross Z, such that X minus Y is a natural number. Now, we can convince ourselves that R is the relation greater than on the set of integers, right? And we can notice that 5, 2 is in R, since 5 is greater than 2, right? i.e. 5 minus 2 equals 3, which is an element of the natural numbers, right? This is how we establish our members of the set. Now, if we flip this, 2, 5 is not an element of R, since obviously 2 is not greater than 5. So, i.e. 2 minus 5, which is negative 3, which is not in the set of natural numbers here. Okay, so what we would write here for this scenario is that 5 is related to 2, if we wanted to use our generic notation of a relation here. And what we would write here is 2 is not related to 5. Okay? Okay, let's look at another example, still continuing on from the book of proof. The relation, and I'm going to now, from here on out, call the relation by the symbol here. the relation on a set X is 1, what we say reflexive, if, and I'm going to write these in shorthand. If for any X in X, then X is related to itself. Here. 2, the relation is symmetric if for any x, y in the set with x related to y, then it must be the case that y is related to x. So what the first one is saying is that the ordered pair xx is part of my relation. And what the second one is saying is if xy is part of my relation, then I can use the symmetry and know that yx is part of my relation as well. Okay, then finally, the relation is transitive if for all x, y, and z in x, with x related to y and y related to z, then it must be the case that x is related to z. Here. And I like to think of this as skipping the in-between. Right? We have our connector, x is related to y, y is related to z, so we can skip the in-between and argue that x is related to z. Okay, let's look at example 11.8. And again, this is from the book of proof. We're on page 208 here. So let n be a natural number. The relation congruence mod n, which you may have seen and dealt with before, on the set of integers is reflexive, symmetric, and transitive. Okay, so now those of you who have taken our MA 630 class, we talk about relations and what we're going to soon define equivalence relations. So hopefully this is just a refresher here. Okay, so let's prove this. So prove. So to show, well, let's remind ourselves here, actually before we prove it, because it may have been a while since you've seen congruence mod n, let's remind ourselves of some definitions. Some necessary definitions. Okay, so one, if A is congruent to B mod n, then n divides A minus B. here. So that's what this congruence means. It's a division. And let's remind ourselves what divides means. If A divides B, then B equals A times K for some integer K. Here. And I always like to draw the arrow. This always reminds me which way it goes. It goes that way. Here. Right, and this is our divide statement. A divides B here. And there's different ways of saying this, right? B is a multiple of A. Here we can also use that terminology. Okay, so let's prove this. Here, to show congruence mod n is reflexive, right? We need to argue that any integer, right, because it's on the set of integers, is related to itself. So I need to argue that for some x, x is congruent to x mod n. But that means that n divides x minus x, but notice x minus x is 0, and we know n divides 0. So we're going to push through the proof that method. So to show it's reflexive, we can notice that n divides 0, right? And that's easy to show because 0 equals n times 0, and 0 is an integer, right? If you need convincing on this, take k equals 0. Hence, n divides x minus x for all x in z. Therefore, x is related to x for all x in z. Okay, now let's argue symmetry here. Now, to show congruence mod n is symmetric, let x, y be integers and assume x is related to y. Here, right? So I'm going to take two generic elements and assume that one of them is related to the other. Hence, x is congruent to y mod n, meaning n divides x minus y. Therefore, there is some integer k with x minus y equals n times k. Notice that y minus x equals n times negative k. Doing some quick algebra, I can factor out that negative to flip it around, and then I can move the negative, right, divide by -1, and associate that negative with the k. here. Furthermore, negative k is an integer, right? If k is an integer, then negative k is an integer, so that n divides y minus x. This shows y is congruent to x mod n. Here. Okay? And go ahead and give this proof a try. Try to show that congruence mod n is transitive. The book walks you through that if you need a little help, if you need some review on that. It's a little trick, but not too tricky. So fun little exercise here. Okay, and then this leads to the following definition. A relation on a set X that is reflexive, symmetric, and transitive is called an equivalence relation. Here. And we can note congruence mod n is an equivalence relation. This one's fading out here on the set of integers. Here. Okay, another definition, the equivalence class containing A denoted by the following is the subset of all x in X such that X is related to A. Here. Okay, and then an important remark which we will utilize here. This is remark 11.2.3. Let X and Y be sets, and F a mapping from X to Y. Define the equivalence relation as follows. Here. For A, B, and X, we say A is related to B if and only if f of A equals f of B. And I already said this here, really define the relation, but we can see that this relation is an equivalence relation. Here, and you can verify that. Very easy, short proof. equality is an equivalence relation. Okay. Now, if we're back to topology without tiers here. So now we're going to bring some of these concepts into our topological viewpoint. If x tau is a topological space and the following is an equivalence relation, on X, then we can define a space Y, which is this notation, and you may have seen this from an algebra class, X mod the relation, to be the set of all equivalence classes such that X comes from X. Here. Okay, now we can define a projection from X to Y by, well, we could just call it a mapping. We can think of it as a natural projection mapping. We can define a mapping F from X to Y by sending the elements in X to their equivalence class. Then, by forcing F to be continuous, we can see the natural topology to put on Y is called the quotient topology. Here. Okay, and what happens is this is the finest topology for which F is continuous. Okay, so note F is a function from X into the power set of x. So that is it assigns to each point x in x a certain subset of x, and namely the equivalence class containing x. Here, right? Remember that these are subsets, right? They consist of all elements related to this element here. Right? So F is really a mapping from the set into the power set, and it's taking the points to subsets. Here, that's very important to remember here. Okay, so we can think of it as a map that will identify in X what we glue to create Y here. And this is a lot of times why we call them identification spaces here, right? Because what we're doing is we're identifying points, and so we can think of that identification kind of as a gluing to create this new topological space here. Okay, let's look at an example. Now, I'm going to venture off a bit from the book to give a stronger foundation here. I think maybe at this point, the author maybe dives in maybe a little too deep. So, let's look at this example. So let the mapping F be from R to the set of 3 elements A, B, C be defined by the following. F of x is A if x is positive, B if x is negative, and C if x is 0. Okay, so my question now what is tau of y? Here. If this was our quotient map here, then what would our topology on the quotient space be? Here. Well, remember, tau y consisted of all subsets such that the inverse image is open in the original space. In this case, our original space is R. Okay, so let's start looking at some things. Okay, so notice here the pre-image of the set A. Right? Now, again, what do sets look like in our quotient space? F is a function from X into the power set of X here. Okay, so we're going to be looking at elements. So look here. So look at elements in the power set. Okay, well, the singleton set A is an element of the power set, right? Because the power set of this three element set, so maybe off to the side, the power set of A, B, C consists of the empty set, the singleton sets, the two element sets, and then the set itself. Here. Okay, so I'm going to move down the list. So let's check this one. So what is the inverse image of this? Okay, well notice that all of the points that are positive map to this point. So this is going to give me this set. Right? Okay, so notice that this is open in R. So it meets this criteria. So that tells me that this is part of my topology. Okay, let's look at the next one, right? Moving down the list. Well, what maps to B? All of the negative numbers. This is also open in R. Okay, so this is part of my topology. But what do we notice about F inverse of C? We just get the singleton set 0, right? Because only 0 maps to this. So the inverse image only comes from this isolated point. This is closed in R. So not all it matters is that it's not open in R, right? So we're not going to add that to our topology here. So that's not going to be part of our topology. Okay, let's keep going down the list. So we've checked this off. So now let's look at the inverse image of A, B. Okay, well, now I'm looking at both A and B. So this is going to be a union of sets. Here. Right? Because all of my A values map here, all of my B values map here. Sorry, all of my A values come from here, and all of my B values come from here. So it's the union of these sets. This is open in R. So I'm going to include it in my set. Let's continue on. So I've taken that one. So now let's look at A, C. Okay, but AC is the following. And notice that BC looks very similar. Notice that they include their endpoint. These are not open in R. Right? So I'm not going to include them. Okay, so I've accounted for that. And now, what two sets am I missing? Well, we kind of get these for free. So I'll put them over here. Freebies. here, right? F inverse of the empty set, notice, is empty, right? So this is always going to be part, and this is open in R. And then F inverse of the entire set is the entire set, because I get the positive numbers, the negative numbers, and the middle point that puts them together, right? And this is obviously open in R. So here's my topology. Here. Okay? Okay, now let's shift gears and try to look at it using equivalence classes. Similar, but a little bit different, okay? So let's look at this example. So let X be the set A, B, C, D, E, F, and define tau to be the empty set X, A, B, AB, ABC, and ABCD. Here. Now, a good exercise as we get closer to our final exam, review what a topology is. Verify that this is actually a topology. Check all the arbitrary unions and finite intersections. Now, of course, this is a finite set, so there are only finite unions and finite intersections. But we can check that. Okay, so now define the subset A to be A, B, C, and the subset B to be D, E, F. And now what we're going to do is define a relation on here. So let the relation be defined as follows. And this is a relation on X. So we'll say X is related to Y if and only if X and Y are in both, are both in the set A or both in the set B. Here. And this is how we will define our relation. Okay, we can check that this is an equivalence relation. Okay, so go ahead and verify that. You don't have to write a formal proof, but just try to convince yourself that that's actually in fact true. It's reflexive, symmetric, and transitive. Here. Okay, so furthermore, I can look at the equivalence classes here, okay? And notice that these are all equal. here. So I can pick a representative from my equivalence class here. Okay, so what is y? Now, y, which is x mod tau, so going back, remember that we defined this to be the set of equivalence classes where x is coming from x. Here, right? This is how we started this conversation. So we're going to look at this quotient space here. Well, what are the equivalence classes? The equivalence classes are A, B, C, D, E, F, but notice that these three are equal and these three are equal. So the equivalence classes are just A and D, which are my two sets, A, B, C, and D, E, F. Right? And I can represent them as the subsets I've defined. Right? Notice that I've defined these two subsets here. Okay, we can now define a map F from X to Y by F of X equals the equivalence class. Right? So in our case, what do we get? We get F of A is A, F of B is A, F of C is A, F of D is B, F of E is B, and F of F is B. And maybe I should have used G here, not mixing up the letters. But this is the function and this is the element here. Right? So notice that each of these elements is going to a subset. Right? It's into the power set. This is a function into the power set. Here. Right? And I'm going to restrict my notation. These subsets are defined by these capital letters here. Okay, so now my new question. What does the topology look like? What is tau of y? Here. Okay, so remember we said tau of y was all subsets of y such that the inverse image is open. Here, right? Okay, well, what happens now, because of how these sets look, okay, so it's all the subsets of y such that the inverse image. Well, what's the inverse image look like? It looks like a union of all of these equivalence classes. Because notice the equivalence classes come from my elements. And the equivalence classes are part of my set in Y. Right? That by here. Right? So notice that this is just rewriting the statement here. This is what the inverse image under this equivalence relation, this is what the inverse image looks like. Okay, so again, so tau of y, let's start building it. Obviously, it's the empty set and y here. Right? And remember, y is this. Y is this set. We get, these are our freebies. Here. And again, to be a topology, we can remember that we must include the empty set and the set itself. Okay, so now what else is going to be in this set? Well, notice that we map to A and B. So I can start looking at the pre-image. So what's the pre-image of A? Well, the pre-image of A is the set A, B, and C, right? Because what maps to A? A, B, and C. And notice if I wanted to see it as this union, this is the equivalence class of A, union the equivalence class of B, union the equivalence class of C. Here, which actually are all equal, but we can view it as follows here. Right? And this is a subset of X. Now, by accident, I erased our original topology. So let's put our original topology back up. I'll put it down here. Our original topology was the empty set X, A, B, AB, ABC, and ABCD. Okay, now the question is this open in X? Well, notice, yes, it is open in X. It's right here. So this is open in X. So A is going to be part of my topology. And if I look at the inverse image of B, this is the set, right? This is just B. This is the set C, D, and E, which again I can think of as a union of equivalence classes, which is the subset of X. But notice I don't find this in my listing. So this is not open. In X. Here, so this is in fact the entire topology of Y. Here. Okay, this is an alternate way of viewing this under this equivalence relation. Okay, let's look at another example. And I'm sorry this video is going to be a bit longer because, as I said, I've ventured from the book to hopefully give a little deeper understanding here for this concept. So let X be 0, 1 cross 0, 1. And let's define this relation on X by 0y is related to 1y for all y in 0, 1, and 1, 1 is related to x2, 1 for all x1, x2 in 0, 1. Okay, now this is in fact an equivalence relation, and we can actually visualize this here, this quotient space. So I'm going to take 0, 1. This is the interval 0, 1 cross 0, 1. So here's my point 0, 0. Here's my point 1, 0. Here's my point 1, 1. And here's my point 0, 1. Right, the corners. Okay, so now what I'm going to do, this is an identification space. So what I'm going to think of is all of the points that look like this are going to be identified or glued to points that look like this. Well, notice that all of my 0 y's lie here. And all of my 1 y's lie here. So what I'm going to do is I'm going to imagine identifying them. And notice if I imagine identifying this boundary to this boundary and gluing, I would get a cylinder here. Okay, but we have another identification. Notice now that all x1 1's and x2 1's, notice that this fixes the y value at 1, so this is this line. This is this. So what's going to happen is this is all identified to a point in the quotient space, because all of these are going to be in the same equivalence class. So I'm going to shrink that down. So what happens is, when I look at my identification space, I'm going to get this picture. That looks like a cone, because I'm going to glue and then push all of that top to a point. So I'm going to get a picture that looks like a cone. And notice that all of these values will map to this single value. And then this edge and this edge will be a gluing edge, so we can kind of think of a seam right there where we glued. Right, and this is my y, which is my x mod, my equivalence relation here. And this is what we would think of as a cone here. Okay, so now the book defines a general cone. So for any space x tau, the cone called Cx tau 1 over x is the quotient space x tau cross I mod equivalence relation, where I denotes the unit interval with its usual topology, and this equivalence relation is defined on X by X0 is related to X prime 0 for all X prime in X. Here. Okay, so this is a little more general here, but let's try to visualize this. So if I have a space, I'm going to kind of draw my space like a peanut here. So here's my space X, and I want to look at X cross I. So it's a Cartesian product. So what this space is doing is it's making I copies of my space here, right? So, here, right? So it's kind of like I have a slice of bread, and then I'm putting a bunch of slices of bread. So they're the same, but now it's along an interval. And this is my interval, my unit interval 0 to 1 here. So I'm making copies of that. So now this is my X cross I. So this space. And then what I want to do is I want to identify the front face, right? And the front face is my X cross 0. Because that's what I'm doing here. All of my points look like X comma 0. Here, X comma 0. So I'm taking the very first copy and I'm going to think of pushing that copy down to a single point in my identification space. And I'm going to try my best to draw this here. So what I'm doing is I'm going to turn this so that it's horizontal, and I'm going to try my best to draw my peanut horizontal. Okay, so that's the top. So I've now turned this, that's the top here. And what I'm doing now is I'm taking that front face, that black portion, and shrinking it all to a point here. So what's going to happen is visually we can kind of imagine each, because I'm pushing these together, each slice is getting narrower, narrower, and narrower into a single point here. So this is kind of my representative of my cone over some generic space X here. And this is our more classic cone here. Okay, some more examples. A very nice and easy one is if I take an interval and I identify the endpoints. So I define an equivalence relation where the endpoints are identified. I'm going to get the circle. B, if I look at a square and I just identify the edges, I'm going to get a cylinder, right? Because I can just glue see if I identify these edges and these edges. So I'm going to glue and then wrap around and glue. I will get our classic donut, our torus. And then another fun one is if I identify my edges with a twist. This is easier with a thinner piece of paper, and I'll try my best to draw this. And there's a twist here. And this is my Mobius band. So if you take a thin piece of paper and glue the edges, but do a twist when you glue the edges, you'll get this Mobius strip here, or Mobius band here. One last one that's a fun one. As well. Here, this is E. If I take a circle, but I have the inside, so I take a disc, and now if I identify the boundary, so I glue the entire boundary to a point, then when I look at my identification space, I'm actually going to get a sphere, because that boundary is going to be glued to a single point. So that's another fun one. There. Okay, let's look at an example. Let's let X be R with the standard topology. And then we want to define this equivalence relation, it's going to turn out to be an equivalence relation on X by, we say X is related to Y if and only if X minus Y is an integer. Okay, so from this statement here, we can notice that X minus 1 is always related to X for every X in R. Right? It's like this translation. So if we imagine the number line, and we look at 0, 1, 2, -1, right? If I pick a generic X, and I subtract 1, or I add 1, right? Because I can still subtract 1, these are all identified. Right, so really this narrows us down to looking at the closed interval 0 to 1, because all these other points are just shifts and they're identified under this. So what we could do is we could take this bigger set and narrow it down to a smaller set to kind of see what's happening in this identification space. But notice now that because x minus y, if the difference is an integer, well, notice 1 minus 0 is an integer. So in this space, the endpoints are identified. And notice nothing else is going to be identified in this interval. So our intuition tells us and the book introduces some of this notation. This is really S1, the circle. So our intuition, again, trying to go through slowly and convince ourselves, we should eventually end up at convincing ourselves what we would like to say is that the quotient space is a circle. And what does the topology put on this circle? Well, we would like to assume, since the original space had standard topology, we would like to assume that the quotient space lived in the Cartesian plane, R cross R, with the subspace topology. Here. Right? So let's write that down. So our intuition tells us that R mod this equivalence relation should be homeomorphic to S1, which can be thought of as a subspace of R2 with the standard topology. Here. Okay, so oftentimes we would like to have an effective way to be able to identify this quotient space as homeomorphic to a familiar topological space and call it Z tau of Z here. This is so this theorem will help us do that. Okay, now let's write down the theorem, and then I'm going to add a line. I've left some space on that board. Here, and this is not in the book, in this section at least. I didn't see it in the book. X tau, so let X tau, let's try a different pen. This video has been going on, I'm sorry guys, but I think this is very important. Let X tau be a topological space. And this be an equivalence relation defined on X. Let F go from X to Y, which is this quotient space, be defined by f of x equals the equivalence class of x so now let G go from x to Z be a continuous function such that g of x equals g of x prime whenever x is related to x prime, then G induces a map G bar from Y to Z that is continuous. And then we will note G equals G bar composed with F here. Okay, so here's the picture. So we have a space, and then we have our Y, which is our quotient space, and we have our classic mapping F. And what we want to argue is that this space is homeomorphic to some other space, right? We'll call it Z. Well, if we can find a map G that's continuous, that preserves the relation, then what happens is we get a map, call it G bar, such that this diagram commutes here. Right? So this map is the same as this map, then this map. Here. And we can define G bar of x equal to G of x. This is going to be our trick because it preserves the equivalence classes, so it's going to be well defined. Okay, so let's go back to our example. We're not going to go into the nitpicky detail, but so the question is, can we argue that our space, which was R mod this equivalence relation, is homeomorphic to the circle, S1? Well, we have this following setup, right? Here's our F, and so the question is, can we create a map G so can we create this? And I forgot my green was fading out. I need to keep my blue with me. Okay, so what happens is we can recall that any point on the circle can be written as cosine of t sine of t. Right? This is a parameterization of the circle here. So let's try g of t equals cosine of t sine of t. But the problem is that this doesn't preserve our equivalence classes. This property doesn't hold here, because if we consider, if we notice, g of 0 does not equal g of 1, but 0 is related to 1. Here, right? We saw that 0 was related to 1 because we needed the difference to be an integer. Well, 1 minus 0 is an integer. So 0 needs to be related to 1, but under this function, if I plug in 0, I get the point 1, 0, but if I plug in 1, I get cosine 1 sine of 1, which is not the point 1, 0. Okay, so we need to modify. So now our question is, can we modify this? And it turns out that we can by using g of t equals cosine of 2 pi t sine of 2 pi t. Now we're okay, because now g of 0 equals g of 1 here. And you can check that. Okay, so this is much better. So this is going to be our candidate for this function g. So now the question is, well, obviously this is continuous, right, by properties of calculus, right? In Calc 3, we started dealing, well, Calc 2 or Calc 3, depending on, you know, how your calculus was split up. We talked about parameterizations. This is continuous, so this function is continuous. Here. So we've created a g. So now what we're going to do is define g bar as g bar of t equals g of t, because what we're doing now, remember in this space, the elements are equivalence classes, and what we're going to do is we're just going to pick that representative of the equivalence class and send it to this value, and that's okay because this g preserves equivalence classes. Okay, and we can check that this is a homeomorphism. It turns out it is. And so therefore we see that this quotient space is just our circle in R2 with the subspace topology. So I hope this extra little bit, you know, there's a lot of detail in this material. This would essentially be the feeder portion. You know, these ideas would feed into algebraic topology. The book goes a little deeper into some propositions and other statements you can read, finishing off in the topology without tears. But hopefully this gave us a at least semi-decent foundation of this material here, talking about the quotient topology.